So let's go very quickly over the last two examples of extreme values. Here before moving on to Rolle's theorem and the mean value theorem. Okay, so let's look at another problem. So this example doesn't involve a polynomial, so let's try to find critical points of f of x equals sine x plus cosine of x. So here just critical points in general, so it doesn't matter where, just in all of R. But now we're also asked to determine, from this, determine the extreme values on the intervals 0, pi over 2. So solution. So let's try to find where we have critical points. And we have sine and cosine, and we are adding them together, and they're both differentiable everywhere. So the only kind of critical points that we can find are points where f prime is equal to 0. So let's set f prime, which is cosine of x minus sine of x, equal to 0. Okay, so can this happens if and only if sine of x divided by cosine of x is equal to 1. Okay, it can, you may be concerned about what happens when cosine of x is equal to 0. So when cosine of x is equal to 0, that implies sine of x is not equal to 0. So in particular, this can never happen, that the cosine minus sine is equal to 0. Because if cosine were equal to 0, then you get 0 minus something is not 0, and that doesn't give you 0. So we're allowed to divide by cosine at the points we are looking for. So just move sine to the other side and divide by cosine. We're allowed to divide by cosine because we know that the points where cosine vanishes are not solutions to this equation. Okay, so cosine minus sine x equals 0. We move sine to the other side and we divide by cosine and we get this. So this is just tangent of x is equal to 1, so that's the set of solutions. And we did an example that asked us to find this the points of for which tan of x was equal to 1. Actually, before we went online, and we know that this happened when tan is periodic. It's pi periodic, so this happens when pi is equal to when x is equal to pi over 4. 1 is equal to pi over 4 plus pi, and pi over 4 plus 2 pi, etc. Also when we subtract integer multiples of pi. So the conclusion here is that critical points are all the points that form pi over 4 plus n pi, where n is any integer. So it could be something really negative, -2, -1, 0, and then all the natural numbers, 1, 2, 3, etc. Okay, so we found all the critical points. These are all the critical points. Yeah, okay, so we completed the first task. We were asked to find the critical points, and now we have to determine the extreme values on, but now we've reduced the interval which we're looking at now, which is 0 pi over 2. Okay, so what do we need? We need the endpoints. So now to 0 pi over 2 now, endpoints. 0 pi over 2. So what is f at 0 is cosine at 0 plus sine of 0. Sine of 0 is 0, and cosine of 0 is 1. What happens at pi over 2? Cosine of pi over 2 is 0, and sine of pi over 2 is 1. So roles are reversed here. This is equal to 1 again. And now we need to look at the critical points. The critical points there lie inside this interval. Critical points there are in between 0 and pi over 2. For which values of n do we get a critical point? Actually, just for n equals 0. When n is equal to 1, we get 5 pi over 4, which is greater than pi over 2. Okay, so right, so it's that's the way it is. So this is greater than pi over 2. It's already greater than pi. And when we subtract pi to pi over 4, we land outside of the interval again because we get a negative number. Okay, so the only critical point of f inside 0, pi over 2 is pi over 4. Okay. And so we need to record the value of f at pi over 4, which is, and this is something again we did a few weeks ago, cosine of pi over 4 plus sine of pi over 4, and this is square root 2 over 2, square root 2 over 2, which is just square root 2. Okay. Okay, this was the function f of x, sine of x plus cosine of x, and we have the three values. So we put the three values. So endpoints were f of 0 and f at pi over 2. They both gave us 1. Let's see what happens here. For the endpoints and the critical points inside the interval that we're looking at now, which is f at pi over 4, which is equal to square root 2. Oh, sorry, it's just... Okay, and which is bigger, 1 or square root 2? Or square root 2, I mean, if you remember what it is 1 point something, so it's bigger than 1. And it has to be bigger, because if you raise 1 squared, it gives you 1, which is smaller than 2, so you have to raise a bigger number than 1 to square to get 2. So the square root of 2 is definitely bigger than 1, so this is the maximum value. The maximum value, the prescribed interval is square root 2. And these two values here correspond to a minimum value. So we found the extreme values here. 1, which is attained at the endpoints, and the maximum value, which is attained in the interior and is a critical point. Okay, now the last example, quick example, so that to give you the idea that we always maximize and minimize things here when we maximize or minimize things when we are, I mean, when the derivative is 0. So sometimes it happens that the function is not differentiable. This is the case when there is a cusp. So let's look at the function f of x equals 1 minus x minus 1, 2 over 3. So this function on -1, 2. So find the extreme values on this interval. Okay, so what we see here is that, okay, what is the endpoints again? So solution and endpoints. Endpoints. So what's f at 1? F at 1 is 1 minus 1 to 2/3, which is 0. So you just get 1. No, oh, sorry. We were supposed to use -1 and 2. So let me check that again. So f at -1, which is 1 minus 1 to 2/3. So it's 1 minus square root 2 get no 2 squared is the cube root of that. So 4 to the 1/3, and then f at 2, and here at 2 we just get 0. 1 minus 2 minus 1, which is 1. Yeah, 2 2/3 is 1, so we get 0. Okay, so that's that's the situation at the endpoints. Right. So what are the critical points now? So the critical points. We'll see. We try to differentiate prime. We get the following: it's minus 2/3 x times 1 over x minus 1 to the 1/3 times the derivative of what's inside, which is just 1. Here, this is the derivative of 1 is 0. And the derivative, this is a power function, the second expression here. So if we had y inside instead of x minus 1, y to 2/3, we differentiate that. We bring the exponent, which is 2/3. We had a minus sign outside. 1 over x minus 1 to the 1/3. This is 2/3 minus 1, which is minus 1/3. Okay, so there's a problem here. So this is not defined. Not defined when x is equal to 1. In fact, it's not only that this expression here is not defined, because that will only show that the derivative is not continuous. I mean, it could be that it was defined, but in fact it isn't. If you compute it by definition, you will see that it doesn't have this function here, even though it's defined when x is equal to 1. It doesn't have a slope, it has a cusp. And so it cannot have a derivative there. Okay, so it doesn't have a derivative there. So this is a critical point. So then x equals 1 corresponds to a critical point. And again, as I said, yeah, so when the derivative is not defined, that is also a critical point. So this is another, not only when f prime is equal to 0, but when derivative is not defined as well. Here we don't have points where f prime is equal to 0. There's no value of x that would make this expression here equal to 0. The only way a fraction can be equal to 0 is if the numerator is 0. Here the numerator is minus 2/3. So that's constant. And we can never find here a value of x that will make this equal to 0. Okay, so the only critical point is the only point which f prime is not defined, so where f is not differentiable. So that's a critical point we get, so we need to record that, and that's f at 1, and f at 1 is 1 minus 1, which is 0 to 2/3, so this is 1. Okay, so we have three values here. We have f minus 1, f at 1, which is inside actually the interval 1. The critical point here 1 is in between minus 1 and 2, right? So it belongs, it's one of the candidates we have for the extreme value. So if 1 is equal to 1. Okay, so we need to compare now the three values, and clearly here 1 is f of 1 is equal to, is greater than 0, and is greater than 1 minus 4 to the 1/3. For the 1/3 is greater than 1 for sure, and 1 so 1 is the largest value. So let's look again. Have everything here. F minus 1 is 1 minus yeah, so here I actually made a mistake. Had minus 2 to the minus 2/3. Oh no, that's okay. So it says minus 2 squared, which is 4. Yeah, 4. 4 to the 1/3. F at 2, which is 0. So these are the values we get at the endpoints. And the critical point, which is in between the endpoints. Critical points, it's only 1 in this case. 1, so if 1 is equal to 1. So this is the max, the absolute max, and this is the min. Okay. The min was attained at one of the endpoints, and the maximum was attained at a critical point. And here the new thing about this example was that the critical point did not correspond to a point where f prime is equal to 0, but where the derivative is not defined. Okay, so that's the point I wanted to make. And then next time we're gonna talk about Rolle's theorem and talk about the mean value theorem. Okay, so we're gonna spend some time on that in applications.